Welcome to qnawire.
We're asked to calculate the value for the equilibrium constant and delta G for three different reactions, and the information that is given directly in the problem is the delta G's of formation for these three compounds. However, in order to properly solve this problem, we also need the delta G of formation for glucose and delta G of formation for water liquid. So the three reactions that we're going to study are, first of all, number one is going to be C6H12O6 plus 6 molecules of oxygen that is going to be in equilibrium with 6 CO2, 6 molecules of CO2 in aqueous media, plus 6 molecules of water liquid. The second reaction that we're going to employ here is the decomposition of glucose, C6H12O6, in equilibrium with 2 molecules of ethanol. I'm going to abbreviate to ethanol to now write down the full formula over here, plus 2 of CO2 in aqueous media. And the final one is going to be the decomposition into lactate, which is going to look quite similar to the last one, but over here we're going to have C6H12O6 glucose that is going to be in equilibrium with 2 molecules of lactate plus 2H+. So in this case, we don't need information for the delta G of formations of H plus and O2. It is because the delta G's for both of them are going to be equal to 0. So first of all, in order to calculate the equilibrium constant, we're going to realize that if we're at equilibrium, the delta G needs to be equal to 0. So that means that delta G naught plus RT logarithm of the equilibrium constant needs to be equal to 0. So delta G naught over RT is equal to the logarithm of the equilibrium constant. And finally, the equilibrium constant is going to be equal to the exponential of, over here with a minus sign on the left hand side, to the exponential of minus delta G naught over RT. After we have found the equilibrium constant, we can go ahead and calculate the delta G for the conditions that are provided to us. Given the following equation, delta G needs to be equal to delta G naught plus RT logarithm of my equilibrium constant. So what we're going to do is do the calculation, show the full results for the first problem, and then you're going to be able to replace the values for the other two directly. So for problem 1, in order to calculate delta G naught of the reaction, we're going to follow the rule that tells us that this is going to be equal to 6 times the delta G of formation of CO2 in aqueous media, which is one of the products, plus 6 times the delta G of formation of water as a liquid, minus delta G of formation of glucose, C6H12O6, minus 6 times the delta G naught of formation of oxygen, which is going to be equal to 0. Remember, whenever we want to find the delta G for the reactions, is equal to the sum of the delta G's of the products multiplied by their stoichiometric coefficients minus the delta G of formation of the reactants. In this case, the result is going to be minus 2,829.8 kilojoules per mole. So now remember that at standard temperature and pressure conditions, the temperature is equal to 0 degrees Celsius, which is equal to 273.15 Kelvin. So that is the temperature that we need to use in the calculation for the equilibrium constant. So my equilibrium constant in this case is equal to exponential of minus delta G standard of the reaction divided by RT, which is going to be equal to the exponential of, instead of minus times minus is equal to plus, will turn into 2,829 98.8 kilojoules per mole divided by R, which has a value of 8.314 joules per mole Kelvin, times my temperature, that is 273.15 Kelvin. Here you're going to realize that we need to transform kilojoules into joules, and the way to do that is that we need to multiply the result, 1000 joules is in 1 kilojoule. We need to multiply by 1000 and then take the exponential. The result from this is, which turns out to be an exponential to the 1245.9, which is, as you can see, a very, very large value, correct? So now let's see what happens when we want to calculate the delta G at 25 degrees Celsius. At 25 degrees Celsius, the delta G is equal to delta G naught for my reaction plus RT times the logarithm of my equilibrium constant. The logarithm of my equilibrium constant is going to be directly 1245.9. So the result that we get is minus 2829.8 kilojoules per mole plus my constant 8.315 joule per mole Kelvin. I need to transform these joules into kilojoules, so I'm going to introduce a conversion factor that 1000 joules is equal to 1 kilojoule multiplied by my temperature at 25 degrees Celsius. This is equal to 298.15 Kelvin. So let's put that value here. Times my logarithm of the equilibrium constant, which, as I mentioned, is, I'm going to put down the multiplication down here just for lack of space, is 1245.9. So, which gives a delta G equal to 258.9 kilojoules per mole. You can verify here that all of the units are going to cancel out properly, and we're summing to things that are kilojoules per mole. And of course, the logarithm of a number is going to be unitless. So now with this detailed problem, I'm going to go ahead with problem number 2, just to see what happens. And since 2 and 3 are almost identical, actually 3 is a little bit more easy because we know that delta G of formation of H plus is going to be equal to 0, then I'm going to leave it at 2. So for reaction 2, the delta G for my reaction, standard for reaction, is going to be equal to 2 times the delta G of formation of ethanol plus 2 times the delta G of formation of CO2 minus delta G of formation of glucose. The values give minus 224.8 kilojoules per mole. Now we're going to repeat the procedure. Remember that the temperature in this case is 273.15 Kelvin because this is 0 degrees Celsius, because this is the standard temperature and pressure conditions, right? So my equilibrium constant is going to be equal to the exponential of minus delta G naught of my reaction divided by RT. This is equal to the exponential of minus and minus turns into plus, 224.8 kilojoules per mole. We introduce a conversion factor over here directly because we know that 1000 joules are present in 1 kilojoule, so that kilojoules and kilojoules cancel out and we end up with joules, and we divide by 8.315 joule per mole Kelvin times my temperature, that is 273.15 Kelvin. Kelvin cancel out, joule and joule cancel out, mole to the minus 1 with mole to the minus 1 cancel out. And with this, we can get directly our result, which is equal to the exponential to the 98.98. E to the 98.98. You can calculate that value if you want in your calculator. It gives something in the order of 10 to the 42, actually 9.66 times 10 to the 42. But that kind of number is not really useful for us, right? It is better to have it in this notation because we know directly that the logarithm of k of equilibrium is going to be equal to 98.98. So with this, we can calculate delta G at 25 degrees Celsius, which is 298.15 Kelvin. And we said that this was equal to delta G naught plus RT logarithm of my equilibrium constant. So delta G naught, we said that was equal to minus 224.8 kilojoules per mole plus R, which is 8.315 joules per mole Kelvin. We need the conversion factor of joule into kilojoules, so 1000 joules is 1 kilojoule. Now multiply by temperature, which is 298.15 Kelvin. Kelvin and Kelvin are going to cancel out, joules and joules as well. And finally, the logarithm of my equilibrium constant, which we said that was 98.98. So with this, the result for delta G is equal to 20.58 kilojoules per mole. Notice that we turned a reaction that was spontaneous into a non-spontaneous one just for the effect of temperature over here. So for the last one, you can repeat the same procedure. I'm just going to give you for the reaction 3 what would be the delta G naught for the reaction, which would be equal to 2 times delta G of formation of lactate minus delta G of formation of glucose, which is equal to minus 122.6 kilojoules per mole. From here, you can follow the same procedure where you're going to calculate the equilibrium constant as the exponential of delta G naught of reaction divided by RT. In this case, you calculate temperature using 273.15 Kelvin, and then you calculate delta G at 25 degrees Celsius, which is 298.15 Kelvin, using delta G naught plus RT logarithm of your equilibrium constant. And that would be all. Thank you very much and have a good one.